Hi everyone, thank you for coming this morning. The topic of my talk this morning is that of invisible galaxies, one of which is in this image. And I can't see it either, even though I've studied it for quite some time. And for those of you that may have attended my talk yesterday evening, the first part of my presentation this morning is going to be very similar to what I discussed last night, and then the second part of my presentation this morning will be very different than my presentation last night, just so that you know what to expect. And the things that I'm going to go over in the next 40 minutes or so are how do we find and study invisible galaxies? If we can't even see a galaxy in an image of the sky, how do we know it's there? And then going on to also think about why do we care that it's there? And what's the connection between these invisible galaxies and dark matter? How can we learn about the physics of the universe by searching for and studying these things? And then I'll spend the second part of my talk highlighting some of the contributions of undergraduate students to the field of studying invisible galaxies, to show some of the things that students can do at the college level and have been doing. And then to highlight how we can bring galaxy studies into the classroom, from the middle school classroom all the way to the advanced undergraduate classroom, by exploiting current and future large sky survey data that are publicly available online. So to put the study of invisible galaxies in context, I'd like to give a little visual tour of galaxies in the universe. And so most of us are used to thinking of galaxies, something like the Milky Way, a large fancy spiral galaxy. But most of the galaxies in the universe are actually dwarf galaxies, galaxies which have far fewer stars than the Milky Way itself. And even though there's just sort of a single bucket term to refer to galaxies that are maybe 1/10 or fewer stars than the Milky Way, dwarf galaxies span a huge range, 5 orders of magnitude, a factor of 100,000 in their star content. And here's a picture of the Large Magellanic Cloud, which is one of the more luminous, this is sort of the upper limit of what you might call a dwarf galaxy, and this is 1/10 of the Milky Way's luminosity. And if you're in the southern hemisphere and it's clear at night, you can see both the small and the Large Magellanic Clouds with your naked eye. And these are galaxies that orbit around the Milky Way. I could step down the dwarf galaxy hierarchy to something that's only about 1/50th of the Milky Way in terms of stellar content. And this galaxy, NGC 205, orbits around the Andromeda Galaxy, and we see it has a very different appearance than the Large Magellanic Cloud. It's a lot smoother looking than the Large Magellanic Cloud, and the color of the starlight we see is much redder than the blue light we saw coming from the Large Magellanic Cloud. And the differences in color is a result of the different temperatures of the stars that are emitting most of the light. And black body radiation tells us that cooler stars emit more red light, hotter stars emit more blue light. So cooler stars are supplying most of the light of this galaxy. These are stars that are relatively older. We can step down again to a galaxy that's only 1/300th of the Milky Way's luminosity. It's still pretty clear in this image. You'd probably still look at that and say, okay, sure, that's a galaxy, I believe that. And this is a little blue fluff ball. It's in our local galactic neighborhood, although not orbiting the Milky Way. We see this as a very blue galaxy. There's a lot of star formation going on. And when we start looking towards the outskirts of this image, a lot of the stars, a lot of these dots on the outskirts of the image are actually Milky Way stars between us and the Sextans B galaxy. And you'll notice that the names of these galaxies, I'll just step through a couple more, tend to have the name of a constellation on them. Leo 1, Leo is a constellation. The galaxies around the Milky Way and in the Milky Way's neighborhood are named after the constellation that they're in the direction of the sky. So Leo 1 is the first dwarf galaxy around the Milky Way that was discovered towards the constellation Leo. And this image looks a little bit funny. There's a very bright star off the edge of this image that's causing these artifacts here. But we can still see, even though this is only 1/3000th of the Milky Way's luminosity, we still very clearly see Leo 1. We see it's got a granular appearance, where that granularity is because the galaxy is close enough and diffuse enough that we can pick out individual stars belonging to it. We can see some are redder and bluer, some are brighter and fainter, which is information that we can exploit to learn about the histories of these galaxies. Leo 2 is only 1/15,000th of the Milky Way's luminosity. Again, most of these stars are in the Milky Way between us and Leo 2. This bright red star is between us and Leo 2. It just happens to be in front of it. We can see very clearly this granular collection of stars showing us the galaxy. And then Draco is the bottom of the barrel. This was the least luminous galaxy known in the universe for 50 years. Draco is about 1/50,000th of the Milky Way in terms of luminosity and star content, and it was discovered in the 50s. by very careful visual inspections of photographic plates taken of the sky. And if you're having any trouble seeing that there's a galaxy here, you can imagine roughly what's the density of these stars in the outskirts of the image and compare that to the density of the stars near the center of the image. And you hopefully notice that there seems to be about more stars per area here than there are here, for example. And that visual overdensity of stars is showing us the presence of the galaxy. And additional observations, such as spectroscopic measurements that show how the stars are moving and what their compositions are, and looking very carefully about the distribution of star colors and brightnesses, confirm both the presence and the detailed history of this galaxy. And so for dozens of years, for decades, many students wrote many dissertations on galaxies just like the ones that I showed you. And it's always been the case ever since dogs, people, whoever looked up in the southern hemisphere and saw with their naked eye the presence of the Magellanic Clouds. It's always been the case that the tiniest galaxies known in the universe are the ones that are very close to us, because it's hard to see faint objects as you put them farther away. And here shows just a little cartoon of the Milky Way disk and the fact that we have this extended halo with small galaxies in it orbiting around us. And the primary focus of past studies of these galaxies before the turn of the 20th century, into the 21st century, had been, just as I've already described qualitatively, is looking at those brightnesses of the stars and looking at their colors, and using those to figure out what the formation history of those galaxies were over the previous 10 million years. But in 1999, a cosmological revolution started in the near field. And at this time, theoretical studies and simulations of galaxy formation were published that definitively predicted, I think that there should be more of these little galaxies orbiting the Milky Way than we've seen so far. And this prediction came directly from a model where the mass content of the universe, there's more dark matter than there is protons, neutrons, and electrons. There's more dark matter than stars, there's more dark matter than gas, by a factor of a lot. And so it had been known for quite some time that these little galaxies we saw around the Milky Way, their observed properties couldn't quite be explained just by the mass there from their stars. You can measure the velocities that each individual star in the galaxies are moving with, and then you can calculate the kinetic energies of the stars in the galaxy. And then you can say, well, how much potential energy needs to be there for these stars to be gravitationally bound to each other? And then you can ask, well, is there enough mass to give us that much potential energy? And if you just look at the stars, there's not enough mass. And this is the evidence for dark matter in the universe, which we've seen on galaxies of all scales. And all of the dwarf galaxies around the Milky Way had this evidence for dark matter. So people have been looking very closely at these galaxies for the last 15 years with great interest in how much dark matter they have and where might the other galaxies be. And even though we don't know what dark matter is, we can throw it in a simulation, add Newton's laws of gravity, and see what happens after 13 billion years. We have a hypothesis for how much there is, and we have a hypothesis for how that matter was distributed shortly after the Big Bang. And if we let Newton's laws of gravity affect that matter and say, well, where should the mass be around the Milky Way right now in the year 2013? We can make a mass map that looks something like this, where each one of these bright spots shows a high density of dark matter. The darker colors show a lower density of dark matter. And so each one of the bright spots is a gravitationally self-bound clump of dark matter, a dark matter halo. And to give a sense of scale, even though when we look at a picture of the galaxy, we're really just seeing this bright spiral or this bright ellipse that shows us where most of the stars are located, the vast majority of the galaxy is located far beyond its bright extent. The disk of the Milky Way occupies less than 1/1 millionth of its total true volume. And so we look very far away from the center of a simulated Milky Way-like galaxy to see what the distribution of mass looks like. And it's good news that we see that there are predicted to be a lot of these self-bound clumps of dark matter, because we do observe 25 of them to be lit up by a dwarf galaxy. But how can we predict that there's tens of thousands of them, yet we only see 25 of them to be lit up by a dwarf galaxy? And this difference in the predicted number of clumps of dark matter and the observed number of clumps of dark matter has been a really exciting thing for astronomers to pursue over the last decade, and it will be for decades to come. This will be one of the primary areas of cosmological research, because it gives us a great opportunity to learn, not just about dark matter, as in, are there actually tens of thousands of clumps of dark matter around the Milky Way? And where are they located? How many of them are there? And how massive are they? But it also gives us a chance to learn about how galaxies form inside their dark matter halos. How does gas cool and turn into stars? How efficient is that? And what happens when supernovae go off? And a partial solution that's critical to test any of the physics and to test any of the cosmological models is to actually have a complete understanding of what galaxies are and are not around the Milky Way. And when I was a graduate student in the late 90s at the University of Washington, there was a new survey coming online called the Sloan Digital Sky Survey. And this survey is done on a 2.5-meter telescope on Apache Point Mountain in New Mexico. And it's the very first, very wide field digital survey done on optical wavelengths in history. And right now, there's about a third of the entire sky has been imaged with the Sloan Digital Sky Survey telescope. Those images have been processed and turned into lists of stars and galaxies and what their properties are. And any of us in this room can go into the computer and download any of that data at any time. And as a graduate student, and then after that as a postdoc, I took advantage of this data set with my advisor and colleagues. And we jumped into it to try to find galaxies that had not been seen before. And up until then, when looking at pictures of photographic plates, the way you found a galaxy was just by looking at the positions of stars. And do I see extra stars in one location of the sky? So you can imagine that something like this. Here, I have a figure showing, just in some patch of sky, the positions of stars. One dot is one star. Right ascension and declination. This is showing where they are. We don't see anything too special here. But we have more information than just the positions of the stars now that we're in the era of uniform digital surveys, where we're observing the sky in multiple filters. We can see, again, how blue and how red the stars are. And so in this random patch of sky, we could make a plot of how blue and red the stars are compared to how bright they are. And in this color and magnitude diagram, we see that in some random patch of sky, stars belonging to the Milky Way, they're not just random sets of colors and random sets of brightnesses, they follow very specific patterns. And these are dim low-mass stars in the thin part of the Milky Way's disk. Here are stars in the thick part of the Milky Way's disk. And here are stars in the extended halo of the Milky Way. I don't want to study the Milky Way, I want to look for invisible galaxies. So if there was a tiny dwarf galaxy orbiting the Milky Way, what colors and brightnesses would its stars have? Well, we have models for that. We have stellar evolution models that show where we expect stars to be in color and brightness. And these lines show where I expect stars to be in color and brightness for an old galaxy with stars that haven't been very rich. They formed early in the universe. And they're at some specific distance out from the sun. And we see that there are many, many Milky Way stars that have colors quite different than expected for dwarf galaxies. So you can imagine taking your catalog of stars and just throwing away most of them, depending on what their colors and brightnesses are. And so then if I go back and do this color and brightness filtering, and I make another plot showing the positions of stars that are left over that satisfy these cuts, I do in fact start to see a spatial overdensity of stars. And then I can process this image and find a very highly statistically significant blip of light. And I've illustrated this visually to show you the method, to illustrate the method that we go about by finding invisible galaxies. But in fact, all of this is totally automated and we're hands-off. We throw in hundreds of millions of sources, the computer chunks on it for a couple of days, and then we take a look and see if any figures like this end up in our directory. And I'll say when I started doing this, and even when I graduated, there were only about 1/100th of the sky was available from the Sloan Digital Sky Survey. And I didn't really think we'd find anything, but I was really excited to painstakingly quantify the galaxies that did not exist. Because you needed to be able to quantify what we knew didn't exist to really compare with predictions. Because as long as it's just our eyeballs sort of looking and finding galaxies, we don't really have a robust census to compare with predictions. And it wasn't until after I graduated that we discovered the first of these galaxies with this technique. But it was quite exciting, and I think there was roughly a year delay in announcing the first ones, because this Ursa Major 1 dwarf, at 1/1,000,000th the Milky Way's luminosity. There's a big jump between that and the previously known least luminous galaxy at 150,000 the Milky Way's luminosity. We weren't expecting to have that jump. We weren't expecting to find things like this, which is pretty exciting. And again, I go back to this picture with the galaxy that we cannot see, but instead what I do now is I draw with purple triangles the stars that pass that color and brightness filter that we use to find a statistically significant overdensity. And if I were you, I would not be convinced by simply looking at the spatial distribution of these purple triangles. But you can imagine that if you had a statistical algorithm, that it would find that there was a statistically significant excess of stars here. And then you could go to your telescope, as we and others did, get a much deeper image to show that there were a significant number of stars exactly where you expected them in color and brightness. And you can go get spectra of each of those stars, and you can show that they're moving together in space and that they're orbiting around the common center of mass. Around the same time, we discovered another object that was only 1/10,000,000th the Milky Way's luminosity. And actually, if you're at a good screen, you can just see this one in the image. And even though it's far less luminous, you can see this one in the image, unlike the other ones, because it's got a pretty small physical size. Those stars are a bit closer together on average, even though there's fewer than them. And I was at NYU at the Center for Cosmology and Particle Physics when we discovered this. And so there were a lot of particle physicists around, and a colleague, oh, particle physics guy, come in here. Can you see anything in this image? And he pointed right at it. And this was actually how we convinced ourselves we discovered the first one. And it's the thing that helped us get over that. They shouldn't be something that's 1/10,000,000th Milky Way's luminosity. But the particle physicist sees it in the image. So it must be there. And we went to the Canary Islands. And I went to the Canary Islands just a couple months later with a person who's my now husband, with a colleague of mine who's a Spanish scientist. They drink a bottle of wine there before observing its observatory. You're not even allowed to drink in American observatories. It was crazy. I did not drink. I would fall asleep. But it's a very interesting observing trip, and we confirmed the presence of this by getting a deeper image of this candidate dwarf galaxy, which somewhat embarrassingly, although I owe some of my notoriety in my career, bears my name for being the very first example of this object to have been discovered. And since these discoveries in 2005, there have been roughly a dozen more invisible galaxies found orbiting the Milky Way. And it's really exciting. We had no idea these existed until 2005, and they might be the most numerous type of galaxy in the universe. We do not have the observations yet to test that hypothesis. Because not only can we only see these around the Milky Way, we can only see many of them quite close to the Milky Way. We can't even see them all the way out to the edge yet. So it's hard for us to know to what extent they only exist because the gravity of the Milky Way has somehow shaped them to be so. Or if the entire universe is just bursting full of these tiny invisible galaxies, which are very interesting test beds for the physics of galaxy formation because those shallow potential wells make them very sensitive to things like supernovae that go off in galaxies of all scales as they're forming. So I'm going to step back and summarize what all the properties are of these ultra-faint galaxies that have been discovered in the context of both all of the Milky Way dwarf galaxies and in the context of Andromeda, our near neighbor dwarf galaxies. And we see the luminosity of the dwarfs in the units of how luminous the sun is. So we see things with less than 1,000 times the luminosity of the sun. These are the things I'm talking about that are 1/10,000,000th of the Milky Way's luminosity, all the way up to 10 million times the luminosity of the sun. And physical sizes ranging from about 100 light years to 3,000 light years in radius. So one thing again to notice is that there's a factor of 10,000 spanning these dwarf galaxies that orbit the Milky Way. The ones that have been discovered in the Sloan Digital Sky Survey are all in the relatively lower luminosity end of this. Here is the location of Ursa Major 1, the object whose discovery I already highlighted, and here's Willman 1 down here. I'll highlight a couple of other of these objects, Ursa Major 2 and Segue 2, that are among the dwarf galaxies that my undergraduates have been studying as well. I'm going to zoom out on the same exact figure, and the color points remain the same. They're the dwarf galaxies that are orbiting around the Milky Way and Andromeda. And I'm going to add star clusters, old star clusters, onto this figure. Because if you're sitting there thinking, why are we calling these things galaxies? And you'd be thinking, well, a lot of astronomers were thinking upon their discovery, why are you calling them galaxies? I think the time is somewhat past, although I still very understandably get a hard time from folks. Why are you calling these galaxies? And quite frankly, up until the discovery of objects like these ultra-faint dwarfs and some other unusual objects and other environments in the universe, the practical definition of a galaxy is I know a galaxy when I see it. Because you can see here that there's a gap in size between this class of objects and this class of objects. And you can call them Fred and Joan, it doesn't matter what you call them, but these seem to belong to two different sets of objects. Something physically different happened to form them. Here's a very unusual star cluster here. But as we started discovering lower and lower luminosity star clusters in what we're calling dwarf galaxies, there was no longer a clean separation in size and luminosity. And this is nice, actually, because it forces us to ask, why are we classifying these things in the first place? What is our goal? It forces us not to use mere appearances, as you might do if you have a stamp collection and you're just sort of sorting stamps. It forces you to ask what is physically different about these two sorts of objects that we can use to classify them. And so there are different ways to approach this question, and a colleague and I postulated a couple of years ago in a paper that came out that we should define a galaxy to be a self-bound, a gravitationally bound stellar system, or a gravitationally distinct system with stars, okay, fine, whose properties cannot be explained by a combination of visible matter and Newton's laws. And if you think that dark matter dominates the universe's mass budget, then you can rephrase this as saying, oh, a galaxy is a bunch of stars that have dark matter associated with them. But if you want to say, well, you know, dark matter is just a theory, I like to pursue alternative theories of gravity, or try to think of alternative explanations, then you can say, okay, I'm going to call a galaxy things where Newton's laws seem not to totally explain my observations. And our motivation for proposing this definition was so that the observers would have to do the hard work of saying, okay, can I explain the observed properties of this object with Newton's laws, yes or no? Handing the theorist a set of objects to compare their predictions to. Because testing this classification can be quite hard. And it works out quite well that all of the objects previously classified as a star cluster, simply by I know it when I see it, none of them need dark matter to explain their observed properties. Conversely, all objects previously classified as a galaxy with I know it when I see it do need dark matter or some modification of Newton's gravity to explain their properties. So this is a physical difference. I already described a way that we could use the motions of stars, their kinetic energies, to try to discriminate between having dark matter or not. Do you need more potential energy than the observable mass gives you? A tricky thing is when you go down to these really cruddy little objects, it can be very hard to observe enough stars to accurately weigh the galaxy. And so we tried to pursue alternative ways of saying, is the potential well that I see deep enough to explain the properties of this object? Yes or no? And one way that we've proposed to ask whether or not the observed potential well is deep enough to explain the properties is to consider whether stars in the system, whether there's a star-to-star difference in the iron content of these stars. So what this figure is showing on the y-axis, each dot on this figure is either one dot for a galaxy or one dot for a star cluster. And it shows the luminosity, which is a reflection of how much stellar mass is in the object, from low to high stellar mass. And it shows, is there a difference in the iron content from star to star? Objects down here have no star-to-star difference in their iron abundance, and objects up here have a significant difference from star to star in their iron abundances. And the reason that iron abundance is interesting is because you only get iron in the universe when a supernova goes off. So to have a difference in how much iron different stars have in your system, you needed to form some stars. A supernova needed to go off to make iron. The system needed to hold on to that iron from the supernova and make more stars out of it. So then the second generation of stars would have more iron than that first generation. You need a pretty darn deep potential well to hold on to the ejecta of a supernova. And so we see that there's this clear difference in the star-to-star variation of iron in galaxies and the star-to-star variation in iron and star clusters. We see that around this luminosity here, which corresponds to about 1 million solar masses in stars, that star clusters do start to appear to have a variation in the iron abundances of those stars, indicating that there was more than one generation of star formation, that they could hold on to what came out of a supernova. But once you have about 1 million solar masses of stars, given the sizes of globular clusters, they have deep enough potential wells to then hold on to supernova ejecta. So this is all very consistent with a basic model where all of the mass here is visible, but we need some unseen mass component here to hold on to the supernovae. And this has been applied in 2 cases so far. 2 of these 1/10 million Milky Way luminosity galaxies have been asserted to be galaxies in the literature because of a star-to-star variation in their iron content. It's consistent with their dynamical measurements, but there was large uncertainties in the dynamical measurements. And so I show here just a spectrum of 2 different stars contained within the Willman 1 galaxy. And we see here, this is just an arbitrarily normalized continuum. This is from the black body radiation coming off of the surface of the star. And the black body radiation emitted by the surface of the star is then processed by the elements as it goes out through the photosphere and out through the atmosphere. And depending on the composition of that star's photosphere, different wavelengths of light can be absorbed by different elements. And so we look at how much light is absorbed by iron as it travels out through the photosphere. What are the depths of those absorption lines at the wavelengths of iron transitions? And we can see that this star up here, I should have labeled it, has a bit more iron than this star down here. This is different by about a factor of 10, actually. And we see that these absorption lines are a bit deeper. It can be hard to just pick that out with our eyeball, but if we take a ratio of those two spectra, and we look at the locations of the iron lines, those dotted lines are a bit off, we see that the more metal-abundant one has more absorption of light with the right wavelengths to cause iron transitions. Okay, so a factor of 10 difference in the iron abundance. This had to have a much deeper potential well than could be explained by stars. It is a galaxy. Okay. So, what is one of my favorite parts of my job? I love studying invisible galaxies. I love learning about dark matter. And I really love that I can do it with undergraduate students at Haverford. And that Haverford provides resources for me to do this with a lot of students. So here, I have a couple of pretty self-indulgent pictures showing our majors from 2010 and from 2013. And I was looking at these images last night, and I was counting up how many students I've been observing with, and how many students have contributed in some way to invisible galaxy research. And between these two pictures, there's 19 different students who have either done research with me or come to Kitt Peak on the 0.9-meter telescope to help obtain observations that have been analyzed for invisible galaxy research. And I've tried a lot of different ways to bring undergraduates into this research, and this is my 6th year at Haverford College. And to be honest, it took me a couple of years it took me at least 3 years to start to get it right. My first 3 years at Haverford, I really sort of was running an ideas lab, which was fun, and students learned how to program. But I had a hard time giving a student a project where they would be able to come to some real fruition and feel satisfaction that they had a scientific answer at the end. And I still struggle and fail with that sometimes. But over the last 2.5 years, since we joined the 0.9-meter telescope consortium on Kitt Peak, I've had a lot more success with projects that are based on studying R Lyrae stars. R Lyrae is a type of a variable star that's observed in relatively old stellar populations. Stellar populations older than about 5 billion years old have some small fraction of their stars as R Lyrae. So if you have a galaxy, one of these little guys that has a couple thousand stars in it, you might have 2 or 3 R Lyrae within that can be discovered. And this shows one of the defining characteristics of an R Lyrae star. As a function of time, their brightness varies. And the brightness varies by up to a factor of a few as time goes on. And so you can take an image of an ultra-faint galaxy again and again and again, and you can measure how bright those stars are and how they change with time, and see, are there any stars whose brightness changes with time? And to use those to try to discover previously unseen R Lyrae that might belong to them. And this is a helpful way, a helpful diagnostic for studying these ghostly galaxies that are otherwise quite tricky to study. Because R Lyrae are a standard candle. They all have the same luminosity, modulo what their chemical abundance is, their iron abundance is. And if you know what the luminosity of a star is, and you know how bright it appears to be, then you can figure out how far away it is. So these are a way for us to measure the distances to these dwarf galaxies, and knowing their distance is a critical ingredient to inferring their other properties. We're also now exploring the possibility of exploiting this type of variable star as a way to discover, bless you, invisible galaxies that haven't yet been seen before. And it also tells us a little bit of something about the stellar population and what types of stars they are. It helps us learn about the formation of the halo component of our galaxy from dwarf galaxies. And so this 0.9-meter Kitt Peak consortium it was pretty friendly for us to join. It's about $600 a night for time on Kitt Peak. So actually the most expensive thing is for us to take students there. Then we had several predecessors ago, my astronomy colleague, my predecessor, Lewis Green, donated some IBM stock when he passed away to the college. And this has since formed a fund that can send students on experiences like this. And so that's how we pay for the transportation. But actually joining the consortium is not too expensive. And here we see part of Kitt Peak. This is the WIN 3.5-meter telescope. This is a small half-meter outreach telescope, and that's the 0.9-meter telescope that students have been. I've probably gone there about 6 times, 7 times myself, and taken students maybe 4 of those times. And here's another couple of self-indulgent pictures. Inside the dome here, this is a fun telescope. There's no operator to use. We're responsible for setting up and breaking it down. There's supposed to be a new camera put on it this semester, but up until now, we had to fill a liquid nitrogen dewar every 8 hours, open up the dome, take off the lens cover on this little ladder here. It's great. Students really feel incredible ownership over this data in the project after they've been there. And there's a happy student working on 3 computers, and there's other happy students spending some time in front of the family of Kitt Peak telescopes during the day before we're observing. And the first project that has been published with approximately 8 undergraduate co-authors, we observed 2 of the objects, Segue 2 and 3, which were among the objects circled on one of the earlier figures. So again, to look for variable stars in them, to see if we might be able to figure out how far away are these invisible galaxies. And I have this picture of Segue 3 here, which is actually a star cluster. It's not an invisible galaxy, but I'm showing this picture. Segue 3 is so crazy, it only has about 50 times the luminosity of the sun. But we can see it in this picture just because it's super duper duper tiny. And so all the stars are very, very close together. It's one of the least luminous, if not the least luminous, old star cluster known anywhere. And Segue 2 is another one of these. It's a Willman 1-like object with 1/10,000th the Milky Way's luminosity. And Erin Boettcher, who's now a graduate student at the University of Wisconsin, she led this analysis with several other students and ultimately led the paper. Discovered a couple of variable stars, one of which was confirmed to be an R Lyrae star belonging to the Segue 2 galaxy, which she then used to provide a first robust measurement of its distance, which is pretty cool. About 100,000 light years away. It took us quite some time to get published. It was my first time working in the field of variable stars, and we had a lot to learn from our referees about the literature, which was really quite helpful. And so then we went back to the telescope with another few groups of students and observed a couple of different objects. One of them called Bootes 3, which wasn't in any of my figures because it's thought to be an example of a completely dissolving, disintegrating dwarf galaxy, which is pretty fun. And Ursa Major 2, which is a cool dwarf galaxy because of the invisibles, it's the most elliptical. And so here shows a spatial plot. These contours show the spatial distribution of stars belonging to this object. So we can see there that it's quite elliptical. It's very squished looking. Much more squished than is typical. And so there's a big question, why is it so squished? Is this giving us a hint to why these invisible galaxies are so darn invisible? Maybe it's losing stars. And so a really exciting thing about looking for R Lyrae in this object is, well, what if we find them all across the face of this object? It's almost about a degree across. Well, they're standard candles. We might be able to see if there's a difference in how far away the galaxy is from side to side. And that could really teach us something about the origin of this object. And this project is still underway. There were 4 students last summer working on it. Andrea Gogan, who's a sophomore, is now leading this publication in collaboration with another student. It turns out in Bootes 3 in our 2 pointings, we did not find any variable stars. I think, although a student is still finalizing that for his thesis project. But Andrea and Eric, here's the spatial footprint of their observations of Ursa Major 2, which we obtained over a 3-year period. There was a couple of different pointings, and she and Eric found 5 different variable stars, shown by these colored stars here, compared to the center of this object. And this spans almost the full red ascension range, as we saw in this map here. So it extends out to and beyond the half-light radius of this object. So of these 5 variable stars, she and Eric have classified 4 of them as candidate R Lyrae. This is still in preparation. And she and Eric will both be presenting this at AAS in January. One of the R Lyrae that they found had previously been published. Another one was mentioned in passing in a spectroscopic study saying, oh, this one's kind of weird, maybe it's an R Lyrae. Oh, it is when we see the light curve, which is cool. And then there are 2 others that hadn't been previously published. And so one thing that we can do to interpret these student discoveries of R Lyrae in context is to ask, well, what do these R Lyrae, what do these variable stars look like in Segue 2 and in Ursa Major 2 compared to the other Milky Way dwarf galaxies that have previously been studied in the same exact way? And one way to do this comparison that people have considered before is, well, what's the average chemical composition of stars in the galaxy compared to how long does it take for the stars to vary in their brightness? What's their period of variability in days? And we see these are all different dwarf galaxies. The black points were studied by other folks. Dwarf RLRs seem to follow this pretty nice relation where more metal core stars have longer periods of variability, right? Different metal compositions change the opacity of the star. I haven't taught variable stars yet, that happens in a couple weeks, and so I can't write down the physics quite yet. And so it makes sense that there's at least a qualitative relationship between how long it takes the star to go like this and what the opacity of the material is. Segue 2, that star found by Aaron Boettcher, seems to fall generally along this relationship. Its average iron abundance is extremely uncertain. There's only a couple of stars with a measured iron abundance in it. However, if we put Ursa Major 2 on this figure, it is quite different than the variable star properties of the other objects. So what does this mean? We haven't thought about it at a deep level yet, but it's giving us a hint, again, to how some of the dwarf galaxies, they've had things in common and things of difference as they formed and evolved over the cosmic ages. The last thing I'll just briefly highlight that students are working on, I'm really excited about this. Mariah Baker's a senior doing her thesis on, what if we flip this whole thing around? We've spent all these years trying to find new variable stars in the dwarfs. Can we imagine a future where there is a massive catalog telling us where all the R Lyrae are, before we know where all the dwarfs are? The Large Synoptic Survey Telescope is a project, a ground-based project that is to survey the entire southern sky in a way that will give us such a list of R Lyrae stars, and this should happen over the next decade. What if we have that list of R Lyrae stars? Can we find previously unknown invisible galaxies? Can we find invisible galaxies that actually, for different reasons, couldn't be found with the traditional technique I showed you at the beginning of the talk? And Mariah's just started to explore this, and the way that she's approaching it is to say how many R Lyrae are there in the known dwarf galaxies. What if I simulate dwarf galaxies with a very wide range of properties, big and small, luminous and faint, near and far, and put them into a simulated R Lyrae survey and see if I can find galaxies that way. And the final thing that I wanted to highlight are how we can bring this into the classroom. And everybody in this room is amply aware of the fact that there are tons of pedagogical resources online for both physics and astronomy. There's a lot of ways that we can bring physics and astronomy to the classroom, with many of the fantastic materials available, many of which have been developed by Kevin, and I'm sure others of you in this room. One thing that is slightly unique about astronomy, I think, is the extent to which the actual data that people are doing publishable research with have been packaged up in a way that makes it very accessible to any scientist, any teacher, or any student. To be able to really engage with that, with the research data, I think makes it very exciting, brings it close to the students. And I'll be doing one of the breakout sessions to give folks a chance in the computer lab who are interested to play around with some of these things. And I'll highlight some of the different categories of what I've done in my own classroom, and I'm not sure what might work for you. Students at all levels, from middle school to advanced undergraduate, and to people like me, have a really fun time interacting with projects in the Zooniverse, which you might be familiar with. And the Galaxy Zoo in particular has been wildly successful over the last 5 years or so. There are dozens of peer-reviewed publications that have come out of Galaxy Zoo thanks to the crowdsourced Galaxy classification. So when you go onto Galaxy Zoo, or your student goes onto Galaxy Zoo and you sign in and you classify galaxies after reading the tutorial, your classifications actually go into a database that's used by scientists to learn things that you can't necessarily program a computer to figure out. Right? The universe is messy. We teach students, oh, there's spiral galaxies and elliptical galaxies and dwarf galaxies, and some of the spirals are tight and loose. But the universe isn't clean like that. And so I really like using this in my sophomore classes when talking about galaxy formation, and then asking students to reflect on, what has this taught you about how galaxies are classified, and how we can make generalizations or not about the properties of galaxies. Another thing that I really like having my introductory students doing, and even I have my general audience students do these as well, are sitting down at the computer in class if we have a computer lab that can accommodate it, and using one of the interactive, clickable, zoomable Milky Ways that are out there. There's a couple of different available. This is an image from the Chromoscope, just chromoscope.net, where you can slide through this bar who's up here from gamma ray all the way down to what the sky looks like at radio wavelengths. And the images are images that were done by massive collaborations with specific science scholars in mind that many publications have resulted out of. But you can look through these different wavelength regimes and zoom in and out and pan all around and say, oh, what's that look like? And it's awesome, right? Students are there like, oh, what's that thing? Why does it look like that? It's an image artifact, and sometimes I don't know. Sometimes we figure it out together. And so this is a really fun way that I've had with my general audience and my introductory major students to explore the galaxy. For our upper level majors, all of our students who get an astronomy or astrophysics PhD are fluent in some coding language by the time they graduate. And that's because all of our upper level coursework requires the use of the ideal programming language. You can do it in Python or Fortran or C or whatever you wanted. And it helps being in a small place because there's only 2 astronomers and a lot of control over the curriculum. So our sophomore entry to the major class, everybody's got to write a little code. I write the code, you change a couple lines. I have a tutorial in IDL, I have a tutorial in Linux. We sit down in the computer lab and you work through it. Here's a numerical simulation of the universe. Play around with it, make a very simple figure, x versus y. And then as they get to the upper level, we increase the sophistication of the exercises that you do engage in. We spend class time on it. We have open workshops and office hours outside of class time. Something new I started this year was a workshop to introduce students into this concept of big data, which is coming out in all sorts of science fields, statistics, computer science, and having students use the SQL database query language to access the public soul and digital sky survey data. You can also use a GUI to do it. You can click on one of these. Students can basically just write, give me data and you're here in the sky, and you get it. But to increase the level of sophistication and to make our students see what might be out there in the whole wide world when it comes to data mining, I've started to have them do the SQL query work. And then once students have a basis for this, right now in our galactic class, I then have them write different SQL queries to get SDSS data, to study galactic structure, to work on error propagation, and to simulate observational biases when constructing mock surveys of the Milky Way. And depending on what you're interested in, one could think of different ways to do this. It took me a few years to figure out how I like to do this myself, given my interest in galactic structure. But it's really, really fun to work with the students. And a lot of our majors end up going on into data mining, are starting to go on to data mining, or wanting to get a master's degrees in computer science, and are interested in not just physics or astronomy, but are also interested in data. And a lot of our students are interested in going on to become teachers as well, which is a fantastic thing. And so I just want to highlight again and go back to what my final points are. Invisible galaxies might be the most numerous type of galaxy in the universe, and they hold important clues to the properties of dark matter. We need a complete census of these invisible galaxies to know which of those predicted dark matter halos are lit up by dwarf galaxies. And the question, what is a galaxy and how do we classify galaxies, it's not just a semantic question for cosmologists. In order to properly compare predictions with observations, we actually really need a very strict definition of galaxy that we uniformly apply to new objects that are being discovered. Undergraduates can meaningfully engage in studies of invisible galaxies and galaxies of all type. And in particular, variable stars are sort of bread and butter standard undergraduate science, and we've been able to use small aperture telescopes to look for variable stars in some of the near Milky Way dwarf galaxies. And thanks to the hard work of many folks that have gone out of their way to figure out efficient methods to serve out these research quality data to the public from sky surveys, there are a lot of ways to bring galaxy research into the middle school, high school, and college classroom. And if you want to hear more about that, you can come to my breakout session and play the computer yourself. Thank you very much, and I take questions.
I have a question about the dark matter and the structure of the galaxy. As I understand it, the ordinary things we see in our galaxy, star clusters, solar system, molecular clouds, and whatnot, as the matter collapses, the reason you can get these things is that the matter can radiate away its excess energy. Dark matter can't, so we don't expect to see an excess of dark matter in a solar system or a star cluster. And on the other hand, galaxies apparently are different, and perhaps the dark matter itself is the seed for the galaxy. And I'm willing to sort of believe that, but what I have a hard time believing is that you have this entire embedded pre-existing condition in our big galaxy with these orbiting little bits of clumps of dark matter that form the seeds for these dwarf clusters. Is that what people think? And how can that possibly be? How can the universe do something like that? It seems like a pretty good trick.
Good, and so I'll address two of the comment and the question. And the first comment, where it seems to be different on the galaxy scale, this idea of condensation losing energy. It's not different on the galaxy scale because actually in the very central regions of galaxies, where gas is cooled and therefore condensed, there's not necessarily a higher fraction of dark matter to stars and gas because of that physical fact. And it really is gravity that is bringing the dark matter together. At 0th order, it only obeys the laws of gravity. And it's not a pre-existing condition. When I show this figure, I'll go online so I can't show you. This is not an assertion or pre-existing condition. This is what happens when you make a very uniform volume of dark matter with slight over and under densities that are consistent with the power spectrum observed in the cosmic microwave background, and you press go, you end up getting structure that naturally coalesces in the form of a cosmic web in the form of filaments. And over time, there are nodes in this cosmic web that, after very early cosmic times, had a slightly enhanced overdensity of matter compared to the other regions, and gravity draws these self-bound clumps of dark matter. So very early on, you get the very fast formation of many tiny dwarf galaxies. They coalesce gravitationally, and big galaxies are formed out of this hierarchical buildup of small galaxies gravitationally merging into much larger ones. And so if we really zoom out from that other picture that I was showing you, this is what the overall predicted matter distribution looks like at the present time. This bottom panel here is even very zoomed out compared to the single prediction for a Milky Way-like galaxy that I showed you. This is a 10 billion particle simulation. It's really pretty bananas, showing I forget how many gigaparsec on a slide or something. And you have this filamentary structure. This is not a pre-existing condition. This looks, to our eye, it looks smooth when the simulation starts. Newton's laws of gravity make it like this. Another question?
Around maybe galaxies around other galaxies that are further away?
Yeah, so dwarf galaxies have been seen in many different environments in the universe. And I'll just briefly go back to the figure showing the demographics of dwarf snow. So outside of the local group, we are able to see dwarf galaxies that are at the very high luminosity end. So fornax here, people often refer to fornaxes around other galaxies. We know about a lot of fornaxes around other galaxies. And the Magellanic Clouds are sort of way over here. We know about a lot of Magellanic Clouds out to fairly far distances from the Milky Way. So using the Sloan Digital Sky Survey even, people have looked at Milky Way-like galaxies at larger distances to try to assess the properties of their dwarf galaxy population. But often what is done is you might take 100 Milky Way-like galaxies, sort of stack up the properties, knowing that you can only see, you might get down to like a Leo 1 or a Sculptor for the relatively near ones. You might only see dwarf galaxies down to these luminosities.
I guess that's the secondary part of that. You don't worry about using undergraduates to detect those further away galaxies at all, or is it really just useful for the ones that are closer to the stars?
To look for aura Lyrae and the relatively more distant galaxies, or to use the color and brightness method to find them?
Color and brightness.
Very good. And so to use the color and brightness method, individual stars in the galaxy have to be bright enough to be seen in sky surveys. And so that's the really limiting factor. So you can imagine, well, what's the deepest I can go from the ground? What's the faintest stars that I can see from the ground? And how far away can that get me in terms of galaxies? And people have been trying to do this sort of counting method for galaxies that are up to maybe a couple megaparsecs away, 3 megaparsecs away with very deep wide field imaging. And I think it's a very exciting next step. There's a technical problem that people are finding, which is that even if you have a sensitive enough image where you can actually see individual stars, as you look at the sky to very faint limits, most of the dots in your image aren't stars. They're unresolved galaxies. And so you have a whole different set of technical issues. So we're really lucky in SDSS era. We didn't even think about it. We got this data for free. Most of the objects in the star catalog are stars. But in the next generation of sky surveys, a major technical consideration will be the pollution of huge numbers of unresolved galaxies that are acting as noise in our attempt to find invisible galaxies. And that's actually one of my primary areas of research right now, is figuring out how to use statistical algorithms to mitigate that contamination. Do you want to say something before I unleash? Thank you very much.